So in the last lecture, we were looking at various molecular orbital aspects of carbonyl functional group. And so now what we'll do is we'll just look at one addition reaction across a carbonyl. So as we discussed, the addition has to happen across a C double bond O, and the C double bond O is quite polarized. And so you will find that, the addition, it's prone to attack by a nucleophile. Okay. So the example of a nucleophile we can take is sodium cyanide. So sodium cyanide is an excellent nucleophile, and it adds to carbonyls quite nicely, and it forms what is known as a cyanohydrin. Okay, so we have discussed this previously in our course, and let's now try and understand the way in which cyanide actually attacks the carbonyl compound. Okay, so let's quickly recap. So there is a carbon-oxygen bond, and we discussed that the pi star of carbonyl is going to look like this. And so you have pi star, which is going to be the site of attack by a electrophile. And now, when you consider the attack, what we may want to think about is that this is one of the orbitals. It's an antibonding orbital, but having a large lobe, it's likely that the electrophile attacks on this lobe over here. Okay, so now if you take cyanide, so cyanide is basically C triple bond N, okay, and it has a minus charge, as we know, and this actually has a orbital that is going to come and interact with the antibonding orbital. Okay, so as we have looked at earlier, so this is the highest occupied molecular orbital of cyanide, which interacts with the LUMO of carbonyl. Okay, so this is the picture that starts emerging when we want to understand how carbonyls are actually going to react. So I'm just going to push this down a little bit so that we can get more space. So the highest occupied molecular orbital of cyanide ends up reacting with the lowest unoccupied molecular orbital of the carbonyl compound, and so that becomes a good starting point for us to understand about stereochemistry of addition and so on. Okay, now what happens after the addition occurs? If you want to do an arrow pushing mechanism, then the way we would want to represent this is that R C double bond O H plus Cn minus. So Cn minus is going to attack here. This opens up, and then it picks up a proton. So you know the rest of the mechanism. So then it picks up a proton and forms R, OH, Cn, and H. Okay, so this is called the cyanohydrin. Okay, so here it picks up an H plus and gives you the final product. Okay, now one of the interesting things about cyanohydrin formation is that this is a reversible reaction. Okay, so if you isolate a cyanohydrin and dissolve this in water, okay, what you're going to get is an aqueous base. So you add some mild base, for example, and what you're going to get back is actually the aldehyde plus Cn minus. Okay, so this is going to be the product. So therefore it's a reversible reaction, and this is just an interesting thing for us to know. And you might have encountered this in your previous course as well. Okay, now let's get back to the attack and let's think about how the attack is going to look like. Okay, so I'm just going to draw the C double bond O again, carbon, oxygen, and here is the antibonding orbital, pi star. Okay, and let's just color this so that we are clear about the signs of the orbitals. All right, now as we looked at previously, the antibonding orbital is at an angle. Okay, so this, for example, is the CO, and if I have to draw a perpendicular here, this is going to be the perpendicular. Okay, and this is 180 degrees, and so this is somewhere in between the 90 degrees and 180 degrees. And so this is certainly not at, it's definitely not at 90 degrees and definitely not at 180 degrees, and it's somewhere in between. Okay. So, this becomes interesting because the lobe that is going to interact with your incoming nucleophile is going to interact at an angle. That is point number one. Okay. Now, experimentally, people are looking for clues about how to understand this whole attack. And there are these two individuals known as Burgi, okay, and Dunitz. Okay, these two guys actually did a lot of work on this, right? So what they did was they went and looked at crystal structures of carbonyl compounds. So they looked at crystal structures of carbonyl compounds, and not just carbonyl compounds, but carbonyl compounds which were crystallized with nucleophiles, C double bond O, and in the presence of nucleophiles. Okay, and what they did was they studied a large number of these compounds, and they found something very interesting. They found that the geometric relationship between the carbonyl and the nucleophile was actually not random. Okay, and there was a definite pattern to this, right? As and when the carbonyl compound and the nucleophile got close to each other, okay, in the crystal structure, and as you know, the crystal structure gives you a snapshot of what happens in the solid phase. Okay, so in the solid phase, the movement of atoms is not very large, and so once it is crystallized, it's going to pretty much stay in that position. Okay, so and also the interesting thing about crystal structures is their thermodynamic minima. Okay, it's not necessarily the absolute minima, but one of the minima that can occur. So combining these two concepts, it looks likely that or it is not unreasonable to expect that from crystal structures one can deduce what are favorable forms of arrangements. Okay, so what they found was that actually the carbonyl compound was not at 90 degrees. It was, in fact, when it was interacting with the nucleus, it was at an angle of 105 degrees. Okay, and so as and when they looked at the crystal structures of nucleophiles in the presence of carbonyls, especially the ones where the nucleophile was close enough to the carbonyl, they noticed that it was not at 90 degrees, but it was at 105 degrees. Okay, so there are two sort of interesting aspects here. So one is the pi star is also not at 90 degrees, and the nucleophile, the angle at which the nucleophile interacts with the carbonyl in solid state, which is called the Bürgi-Dunitz angle, is also not 90 degrees. Okay, so therefore the traditional picture that we understand where C double bond O interacts with the nucleophile at 90 degrees is false. Okay, so it's more likely that it attacks at an angle. Okay, so this is very important because this is something that allows us to understand how carbonyl is going to react. So in addition to these two, that is, number one is the pi star, and number two is the crystal structure, X-ray structures. The third clue comes from high-level computational calculations. Okay, so very frequently, especially in mechanistic organic chemistry, we use computation to support experimental data. Okay, so since the Bürgi-Dunitz angle suggests that it's somewhere between 105, 106, 107 degrees, you can now develop a computational model that can help support this finding. Okay, so all these three put together suggests that the attack of the nucleophile does not occur at 90 degrees. All right. Now, this helps us develop a framework. Okay. Now, before we go forward, we want to understand certain terms. Okay. So now let's look at some terms that are important. The first term that we want to understand is prochirality. Okay, so we already know what chirality is. So now let's look at what prochirality is. Okay, So prochirality is nothing but, it's a center, it's a carbon center or a center that is present in molecules that can become chiral. Okay, so here is the example that we looked at in the previous lectures. So when you add a cyanide to this molecule, you actually end up having a racemic mixture. And so let's look at that structure over here. pH, you have the possibility of CN being front and OH being behind, and hydrogen here plus enantiomer, right? So this is something that we looked at previously, and so I'm not going to repeat this. But this center, which is the carbonyl over here, is called a prochiral center. Okay, so this molecule is a prochiral molecule because it can form a mixture of enantiomers depending on which phase the attack happens. Okay, now a prochiral center can also be defined in a different way. So for example, if I start with glycine, okay, so glycine is nothing but COOH, NH2, and there's a hydrogen here, and there's a hydrogen here. Okay, now if I replace one of these hydrogens with a deuterium, okay, so now if I replace one of these hydrogens with a deuterium, what happens is I get exactly the same molecule, right, except that this is deuterium and this is hydrogen. Okay, so this molecule, this center is actually a prochiral center because replacement of one of the hydrogens results in a chiral molecule. So this, as you know, is chiral. Okay, so just to recap, prochiral center is nothing but a molecule or a center which is symmetrical otherwise, but once you do certain modifications to it, either addition of a cyanide or addition of a nucleophile or replacement of one of the hydrogens with deuterium, you end up with a chiral compound. Okay, so this helps us understand what are the centers that can potentially form new chiral centers. Okay, now we just want to understand how to define these molecules, and so the way we do this is we use similar R/S nomenclature that we are very familiar with by now. So for example, NH2, the same glycine example that we take, so we have one hydrogen here and one hydrogen here, right? And what we're going to do is we're just going to replace this one hydrogen, as we discussed, with a new group. Okay, so when I replace this with a new group, which I'm going to call as G, and what I need to do is I need to figure out whether this is R or S. Okay, so let me start doing the nomenclature. So nitrogen center gets 1, carboxylic acid gets 2, and let's assume that this G has a lower priority than NH2 or COOH. And for example, if G is deuterium, then it's going to be priority number 3. And now if I look at the rotation, this is going to be anti-clockwise, so this is going to be called as S. Okay, so therefore this original hydrogen that was drawn here, okay, COOH, NH2, and this hydrogen, which is here, is actually pro S. Okay, so the reason is that if I replace that hydrogen with deuterium or another group, it's going to form a S isomer. Okay, and as a corollary, if I replace the other hydrogen with deuterium, then I'm going to get R, and so the other hydrogen is going to be called as pro R. Okay, now what about phases? Okay, so these are already tetrahedral centers, but what about sp2 hybridized centers, which we are going to deal with? Okay, so the way we would call this is these are called as enantiomer topic phases. Okay, so we have two phases for a carbonyl, and just to make things easy, I'm just going to draw it in this following manner: C double bond O, pH, and the other phase is pH, C double bond O, H. Okay, so if we are to draw it in this following manner, then this, if I have to number this as 1, 2, 3, then this is going to be clockwise. So this is called the RE phase, and the same thing is 1, 2, 3. This is going to be anti-clockwise, and so this is called the SI phase. Okay, so whether a compound is reacting through the RE phase or the SI phase is something that we can very clearly define. Okay, so in the case of tetrahedral molecules, you replace hydrogen with deuterium and you label them as Pro-R or Pro-S. In the case of carbonyl compounds, you can go ahead and put them in and then just number it in the priority. And if it is going to be clockwise, it's called RE, and if it's going to be anti-clockwise, it's called the SI phase. Okay, so this helps us with precisely defining terms when we go forward. Okay, now let's just do a simple exercise of addition of a molecule. So let's take pH, C double bond O, H. The way I'm drawing this is, if you have to number this priority wise, it will be 1, 2, 3. So this is going to be the SI phase or the C phase. Okay, and now if the C phase reacts, then we're going to get CN over here, OH over here, H here, and pH over here. Okay, so if the C phase reacts, then now I'm going to get this compound, okay, with cyanide ion, right? So that's the example that we looked at previously. So now if I have to number this, then I would get, this is priority number 1, this is priority number 2, and this is priority number 3. And so if I'm looking at it from here, then it's going to be anti-clockwise, but since the fourth priority is towards me, so this is going to be R. Okay, so just to highlight that there is no connection between the C phase and the eventual absolute configuration of the compound. Just to be careful. So C has nothing to do with S, and Re doesn't have anything to do with R. Okay, now what you can do is you can actually work out the addition through the Re phase and write out the product that is formed. Alright, so you are looking at enantiotopic phases. So we have a RE phase and a SI phase, and so this helps us sort of understand that, if addition happens on one phase, you get a particular enantiomer, and if it adds on another phase, you get a different enantiomer. Okay, now we also know that, if you already have a chiral center in the molecule, then if you add to a carbonyl, then you're going to get a diastereomer. Okay, so the first experiment that we're going to do now is we're going to take this molecule here, this MEH, okay, and you get a C double bond O, CH3. Okay, so notice that this is the chiral center, and it's actually quite far away from the carbonyl. Okay, now if you add a sodium borohydride to this molecule, you're going to end up with a 1-to-1 mixture of the product, pretty much. And so, as you know, that there is an RE phase and then there's an SI phase, and the addition can happen on both sides. So I'm going to draw this whole group out as R. So you will get R, CH3. Sodium borohydride is a source of hydrogen, H minus. So you're going to end up with this product, and you're going to get R, C. If hydrate comes from the other side, you get OH and CH3. Okay, so these are the two products that you can expect to get. And this actually is approximately 1:1. Okay, so that means that you get pretty much equal amounts of the two enantiomers. So what it suggests is that the chiral center, which is over here, which is quite far, has no impact on the outcome of the reaction. That means that you're going to get 1:1 in product formation. Okay. However, the interesting thing here is that if I start with a slightly different compound, so I have a following molecule, okay, C double bond O, CH3, and I start with this compound, okay. If we add, sodium borohydride or lithium aluminum hydride to this compound, again, if our previous observation was correct, when we add source of hydride, we should get a 1:1 mixture of the two compounds. Okay, so let me draw out the two compounds over here. So we have pH, Me, the carbonyl over here, and let's say hydride comes from the top face, and so you end up with H. Okay, and now just to be sort of clear over here, we would call this this compound as anti, because these two have, the two functional groups have a anti relationship to one another. And let me draw out the second product that could be formed, which would be following compound, which is pH. The methyl group is over here, and now the addition happens from the other side. So you have OH here, and a hydride is here, H is here. Okay, so just to stick to the same similar nomenclature, so this methyl is over here, OH is over here, so this would be called as a syn. Okay, this is again something that we are already familiar with. Okay, so you have a mixture of syn and anti products. The only catch here is that the ratio of these two products that are formed is not 1:1. Okay, so what we would expect based on the previous experience is that you should be getting a 1:1, but you actually end up with a 3:1 ratio of anti to syn. Okay, so this observation is very interesting because as the chiral center moves closer to the carbonyl, you seem to have an impact on the outcome of the reaction. Okay, so in order to explain this, we need to be able to first understand certain concepts. Okay, so we will take this up in the next lecture.